And the first presentation comes from Max Versace from Neurala. And he will give us a talk about how deep learning and vision AI are revitalizing manufacturing. So, Max, stage is yours.
Thank you.
We're looking forward to your presentation.
Thank you so much. Can you guys hear me? Awesome. So we're going to talk about deep learning today, and welcome. And I don't know if you are like myself, but I have the unfortunate habit of watching the news. And most recently, this is what I found while reading the news that touches our industry. Disruption of supply chain, pandemic, boosting automation and robotics, and automation and robotics maybe being bad news from workers. And you think that's all there is about our industry, and that's what our focus of attention is. But really, what has been going on in the industry is much older challenges that have been underlying the manufacturing space for many, many years. Out of COVID is just the last one that came in, but pressure to improve has always been there. Reshoring is a more recent tendency of factories coming back to US and Europe. Increasing SKU offering, so creating additional complexity for the manufacturing. And all of these challenges cannot be met most likely with adding people. People are hard to find, and manufacturing has a waning workforce, so the number of people employed in the sector is a diminishing return. High cost, humans always have an high cost for employers, and more humans doesn't solve problems of high errors and lack of data logging for the manufacturers. So let's talk about a specific task, which is the task of visual inspection. Of course, we are at the vision show. We all know what this is about. Quality inspection is checking if the product is right or not. And let's look at some numbers here to give you some context. 10 millions is the average cost for a food company recall. So they're very expensive problems. 50 millions is the record-setting number of vehicles that have been recalled for electronic components defects. Out of this, we have about 350,000 people working in US in 2020 in the quality inspection process, which is a waning workforce. 47,000 is the projected return, projected reduction of this workforce in US, and the 100 millions is the projected number of US manufacturing machine vision systems to be deployed by 2025. So it's obvious that the diminishing workforce is being met by adding more and more automation. So that's great, and that's where deep learning comes in. And the brain up there is what I've been working on for about 25 years, at the beginning in academia and now with my own software company. And there is a shared set of problems and solutions that whatever we have in our skull, those 100 billion neurons and 250 trillion synapses can do for the manufacturing sector is very, very relevant and very timely to meet the challenges that we just talked about. So from each camera requiring a human operator, or for each machine requiring a human operator to understand what's going on, we are moving into a scenario where each one of these cameras, each one of these machines will have their own brain, which is fundamentally coming from the R&D that has been done by people like myself for the past 20, 30 years in academia. And this gives this camera and this machine the ability to learn just from example like we do. I show you a chair and I tell you this is a chair, and you're able to learn it very quickly without much supervision. And you can do this today in a very lightweight software. So with a software solution that is very simple and very easy to implement for everybody. So what's the difference between traditional machine vision that has been going on for the past 20 years and deep learning, which is a new word for a very ancient technology called neural networks? When I joined the field, deep learning didn't exist as a name. The real name for this sector is actually neural networks. And the difference is very simple. In the traditional machine vision or traditional AI case, you use the intelligence of the operator to create a sort of a flow chart based on explicit feature that somebody can program, and to say this cap is defective or not. Whereas in traditional deep learning or neural networks, all the intelligence the scientist is encapsulated in the mathematical equation that describe the relationship between these neurons and synapses. And the system can learn by itself to distinguish a healthy cap for a wrong cap. So it's a data-driven approach where the solution is able to distinguish out of the visual input just with data. And that's a fundamental difference, and that's an incredible evolution with respect to how things have been done in the past 20 years. So we started, of course, with inspection 1.0, which is the manual inspection with the operator looking at products. This is expensive to do, inconsistent in quality, inability to identify defects invisible to the human eye, right? You cannot put a person inside a tiny industrial machine, and lack of traceability. So it's always very artisanal. And then there is the 2.0 is the traditional machine vision, which all of us know pretty much for the past 20 years, requires expertise, is hard to implement, it requires time, which is equivalent to requiring money. And then there is the 3.0 version, so it's an ever-expanding province of applicability that deep learning is conquering with respect to traditional machine vision. Has human-like ability to do qualitative judgments, which are really hard to do with traditional machine vision. The ability to be trained just with showing good products, which again is a difference fundamental with respect to traditional machine vision. Some of these products are easy to use, no PhD required, and cheaper to set up and operate, and have the ability, the potential to do 100% inspection of your products. So that's great. Why isn't this everywhere? Well, as I mentioned, not all solutions are easy to use. So the number of PhD worldwide is a very thin category. It still takes 4 years to get a PhD in AI. I can tell you that. There are no shortcuts, so you have to study. And out of the 36,000 self-reported AI experts in AI, just a small percentage actually knows what they're doing. Traditional deep learning or traditional neural networks need large quantity of data to be set up and deployed, and it's costly. Some of these solutions require GPUs, which you have to compete with Bitcoin miner to be bought and implement. So what companies like the one I'm leading have been working on is to lower the bar for this technology to be accessible to everybody. So I like to think of the metaphor of WordPress. WordPress, if you guys remember the early times of the internet when you had to learn HTML to build and design and deploy a website, what the AI industry needs in manufacturing is something as easy to use as WordPress, where everybody with zero expertise in internet or designing website, or in this case building AI, can design, deploy, and maintain this solution without any expertise, lowering the cost barrier, lowering the expertise barrier, and opening up the floodgates for this AI to be applied everywhere. And that's what my company has been doing. My company called Neurala has designed such a product, such WordPress for AI, that has very, very little understanding of AI required, actually zero, where you collect some images, you train a model in seconds, and you deploy it and inspect on the production line, interfacing with any gigi camera, PLC, any industrial PC, using just tens of images, right? So you can do this in 5 minutes. We actually have a stand in this hall where you can see that being done. And fundamentally making it quick, easy, and really inexpensive to design and deploy these models in seconds. But I think that the proof here is in the pudding, so let me show you actually what has been done in the field with this technology. We have solved, with the WordPress for AI, the classification of food trays to understand whether these food trays that you buy at the grocery store or you bring in, for instance, in hospital and nursing home, have all the right ingredients before being sold. Baby wipes, are they packed correctly before they hit the supermarket? Is the dog food contaminated, which is a very hard problem to solve? Is there any contaminants in the dog food, or are the surface of these plastic components okay? So let's talk about the first application, Appetito, which is a German, UK-based food company. It's a company that prepares 1.4 million meals per year, so very high number of products, very large number of SKUs, so 1,200 SKU in 14 production lines. The products vary constantly, so it's very hard to design one solution that fits them all. So you have to have something that can be trained on-premise very quickly on new products. And what they want to do is to reduce complaints. So they have about 1,000 complaints per year due to missing food components, and they want to be sure that the tray contains all the right components before being sold. So this solution is being fielded and is solving today the problem, doing 100% quality inspection and 100% accuracy in detecting the trays that contain, in fact, the right products. The second deployed solution is in a couple of dozen factories worldwide, and it's a Fortune 100 food company that has the problem of detecting contaminants in food. So in order to be able to detect a contaminant, you have to have a fairly versatile solution. A contaminant can be anything. It can be the finger of an operator, hopefully not. It can be a piece of plastic, it can be metal. So it's an ill-posed problem, which is very hard to solve with traditional machine vision because you don't have a recipe. You cannot calculate all the contaminants that can be found in a specific slab of meat. So you have to be able to detect an anomaly, which to a human is really simple. I look there and I see something that doesn't belong there and say that's an anomaly. So it's very easy to do with AI, but it's extremely difficult to do with traditional machine vision. So that's a product that is being deployed in over 20 lines today, again solved with machine vision. And then I like just to point out that you cannot lower the barrier for artificial intelligence to get into many applications unless you also make it really inexpensive to do so. And so that this camera, which actually is demonstrated today in the Teledyne FLIR, which is a partner of our company, is breaking the barrier of a few hundreds of dollars to have an AI-enabled camera that actually has the AI running directly on the camera without requiring an external processor or an external industrial PC to run. So this is the Firefly DL. DL stands for Deep Learning. Is available today and has a Movidius chip inside, which is a neuromorphic chip. Neuromorphic means neuromorphe, or of the shape of neurons. So it's one of these neuro-inspired processor that enables this camera to have AI installed directly in the device for training or for deployment without requiring external computing resources. So this is important, again, to lower the barrier and to enable this camera to enter, for instance, inexpensive machines where the total cost of the machine, the total bill of material is just a few $1,000s. You cannot pay $3,000 for a camera. You can pay a few hundreds, and this enables this AI to get into these applications which are today forbidden for the high cost. So I just show you a little bit of a flavor of where deep learning can be deployed. All of these applications that are shown here on the screen are applications where either we have already a deployment or we have a POC that is leading to a deployment. It's very important to notice that not only different industry from electronics to food, which are radically different in terms of the type of inspection you're doing, but we are talking also all the various phases of the production, from the intake of raw materials, right? The dog food case was raw meat. More raw than this, you can't, all the way to production, packaging, and palletization and shipping. So everywhere in the production line, from the intake all the way to the shipping, AI is now either applied or in the phase of deployment. And so it's a pervasive technology that is making it everywhere. And at the end of the day, we have to be realistic, right? This is all nice and fun, but if it costs too much money, it's impossible to go to a customer and propose a solution that doesn't meet the cost criteria. So in case of a recall, we have to calculate, well, what's the cost of a recall? As we have seen for a food product, it's maybe $10 million, but then it takes time. That's another cost, reputation, and there are other hidden costs for a recall, for a bad product. And today we can deploy this solution between $10,000 to $200,000, depending on how complicated is the machinery that has to do the inspection, to fundamentally propose something to the manufacturer that have no problem in accepting, because they know the cost, they know how much the AI costs to them, and so it's really a no-brainer, if you allow me the term. So just to summarize, we are at the inflection point where the hardware, the software, and the use cases and the total cost of the solution makes it viable for AI to enter and never leave the field of manufacturing. So there is no return. AI is here to stay, definitely. Powerful deep learning technology, usability by every operator, and economic viability. So hopefully I gave you a little flavor, and happy to take any questions, and thank you for your attention.
Thank you, Max.
Questions here or after?
What?
Questions after or?
Questions after, yeah. So please, no. Please.
Oh, here,
stay
okay.
Here. Thank you very much for your presentation. I really like that you pointed out the basics and give an overview to come along with the topic. I really like that within such presentation.
Thank you.
So the room's open for questions. Are there any questions? Yep.
Thank you so much for the presentation. I was wondering about the neuromorphic chip and the fact that it can train the model on the camera. It's very impressive. I was curious to know if it can do this training while doing inspection, or it has to stop before starting the training.
Yeah, so normally you do the training before an inspection. Although you're pointing out a very interesting feature, because in our technology, the technology my company has actually developed, enables you to do the training while you do a classification, right? So the way humans are able to learn is actually there is this distinction in the literature between training and inference, right? Inference is when you have a trained model that you can infer with or you can understand with, whereas training is usually separated. In humans, this is conflated, right? So when you're now listening to me, your brain is doing an inference because you're understanding, hopefully, despite my accent, what I'm saying, but you're also learning what I'm telling you at the same time, right? So there are very few technologies that enable this to happen in a single tick. When the network is doing one tick, one inference, you can also do the learning. Normally, for procedural sanity, we distinguish these two processes because the manufacturer wants to know that they have a golden model, that they know they work for that particular product, and then they train it, and then it's ready to do the inference. So usually we separate these. But it's important to be able to do the training without an industrial PC, because you don't need the industrial PC.
Right.
And so it's a cost that you don't have to eat.
Great. Thank you so much for answering.
Okay, thank you very much. Are there another question? Then I have a last question. Can you say a little bit more in detail about what's behind this mighty AI processor?
So neuromorphic processors have been studied and developed for many, many years. Actually, if you guys have a cell phone that is the latest generation, you most likely have a neuromorphic processor. If you have an Apple phone, a Samsung, or a Huawei, or any of those high-end phones, as opposed to just having a CPU and a GPU that have been around for a while, they start to have so-called NPUs, or neural processing units, that differ from the CPU that is very fast but serial, and the GPU, which has been developed by for essential graphic processing. They differ because they're designed to be most closely mimicking the nature of neural computation, which, as I explained very quickly, consists of neuron and synapses. So the yield of a processor is much higher if you mirror the brain architecture in silicon, mostly for reducing the power and increasing the speed. So just my little company has deployed about 60 million of our software copies in cell phones using neuromorphic processors. And now slowly, because the manufacturing space is a little slower than other spaces like consumer electronics, slowly these new processors are entering the manufacturing sector, and they're being embedded in cameras. And once that happens, it's very hard to go back, right? Because it's very useful to have this processor directly in the camera without having, as I mentioned, an industrial PC, which has the brain, in a separate box, right? So you will see more and more of this camera with this neuromorphic chip being sold in the market in the next few years.
Okay, thank you very much. Okay, then Thanks again.